We're going to do something a little bit different today. It will be a little bit more of an advanced problem. So this is the type of problem that you would see at the very end of an abstract algebra class in undergraduate mathematics or in maybe a first year graduate course. And so I'll probably do these sort of more advanced types of problems maybe on the order of once a week from here on out, just to keep it interesting for me. And in fact, it's kind of in line with my vision of the channel, like in the future, having math of all levels. Okay, so here what we want to do is show that there are no simple groups of order 66 or 144. So I'm going to start at a fairly high level here where we know what the notion of a group is, a normal subgroup, and so on and so forth. I will recall the definition of a simple group. So that's a group that has no non-trivial normal subgroups. In other words, its only normal subgroups are the trivial group E and the whole group. So simple groups play the role of prime numbers in group theory. And I'll also recall Sylow's theorems. So let's suppose that the order of G is equal to P to the alpha times M, where P is a prime and alpha is the largest power of P that divides the order of G. In other words, P does not divide M. So the first Sylow theorem says that there exists a subgroup of G whose order is P to the alpha. Sometimes this is called a Sylow P subgroup. Next, if we have two subgroups of G that have order P to the alpha, they are conjugate. So in other words, there is an element G in G such that G inverse PG is equal to Q. So something that easily follows from this is that if there is only one subgroup that is of order P to the alpha, then it is normal, because then you would have G inverse PG equals G for all G in G. So we're actually going to use that as we move through these solutions here. Okay, next, if we set n sub p equal to the number of subgroups of order P to the alpha, in other words, the number of Sylow P subgroups, then n to the p divides m, this leftover number here, and n to the p, n sub p is congruent to 1 mod p. So this last condition gives you a nice arithmetic way to break down the number of Sylow P subgroups you may have. Okay, so let's do this first one first, and that is if we have a group of order 66. So let's suppose that we have a group G, and the order of G is equal to 66. Notice that that is equal to 2 times 3 times 11. So we know that we have a subgroup of order 2, a subgroup of order 3, and a subgroup of order 11. We don't know how many of each of those we have. But we know that the number of each of those must satisfy this congruence down here and this divisibility condition down here. So I'm going to notice something real quick that actually will not solve this problem, but is useful to notice. So let's say n sub 2 is the number of Sylow 2 subgroups. In other words, the number of subgroups of order 2. So first off, we know that n sub 2 divides 33, because that's the leftover number after dividing the order by 2. And we know that n sub 2 is congruent to 1 mod 2. So that's actually not super helpful here, because all of the divisors of 33 are odd already, which is equivalent to saying that they are congruent to 1 mod 2. Okay, so let's maybe look at n sub 3. So n sub 3 must divide 22, and n sub 3 needs to be congruent to 1 mod 3. So notice that that tells us that n sub 3 can be in the following set. So it could be equal to 1, or it could be equal to 22. So from this condition, it has to be a divisor of 22. That's 1, 2, 11, or 22. But then by this condition, it needs to be 1 mod 3. So of those divisors, we're only left with 1 and 22. Okay, so if it's equal to 1, then we have a unique subgroup of order 3, which means it is normal, which means our group is not simple. If it's equal to 22, then all bets are off. Okay, so let's maybe look at the very last case, and that would be the Sylow 11 subgroup. So notice that n sub 11 must divide 6. That's because that's what's left over here. And n sub 11 needs to be congruent to 1 modulo 11. That means that n sub 11 equals 1, 2, 3, or 6. But there's only one of those that is congruent to 1 mod 11. So fusing these two together, we see that n to the n sub 11 is equal to 1. So in other words, our Sylow 11 subgroup is unique, and thus it is normal. Again, by a pretty simple exercise built off of this condition right here. Okay, so now let's look at our second case. So we just got done showing that there are no simple groups of order 66. Now we're going to see that there are no simple groups of order 144 either. And this is actually going to be quite a bit more difficult. So let's get to it. So let's suppose that we have a group G, and the order of that group is 144. Now we probably need the prime factorization here to see what type of Sylow subgroups we have. So this factors as 2 to the 4 times 3 squared. So that means we've got Sylow 2 subgroups that are order 16, and we have Sylow 3 subgroups that are order 9. And we have to decide which of those we want to play a game with. And it's actually more fruitful here to look at the Sylow 3 subgroups. So let's let n sub 3 equal to the number of Sylow 3 subgroups of G. And I want to point out that these Sylow subgroups are of order 9. So let's maybe put that here, of order 9. That's what we mean by a Sylow 3 subgroup. It is a subgroup of order 3 to the maximum power that we could get, but that's 3 squared here. Okay, great. Now by this condition down here, we know that n3 must divide whatever left over after we divide out all the 3-ness from the order of G. So in other words, it has to divide 16. And then we also know that n sub 3 needs to be congruent to 1 modulo 3. So now putting those together, that just gives us a fairly small set to check. So in fact, what we get is that n3 is in the following set: 1, 4. Well, 1 is always going to be a possibility because 1 is always congruent to 1 mod p for any prime, and it always divides every number. Notice that 4 is congruent to 1 mod 3, and 4 divides 16. But then the only other one that works is 16. Notice that the other divisor of 16, which is 8, is congruent to 2 mod 3, so that does not work. So let's just rip through these one case at a time. So our first case will be n3 equals 1. So, but if the n3 equals 1, we have a unique Sylow 3 subgroup. And that unique Sylow 3 subgroup, again, by this condition right here, will be normal. So we'll write that here. The unique Sylow 3 subgroup is normal. If that unique Sylow 3 subgroup is normal, then we have a normal subgroup of order 9. That is not the whole group, and it's not just the trivial subgroup. So in other words, our group is not simple. Okay, so let's jump into case number 2, and that would be n3 equals 4. So in other words, we have 4 Sylow 3 subgroups. So let's name them maybe P1 through P4. So let's let, and I'm going to use this notation, SYL underscore 3 of G, to be the set of all Sylow 3 subgroups of G. Let's say that this is equal to P1, P2, P3, P4. Great. Now, I want to do like a fairly common trick when it comes to working with these Sylow theorems, and that is build a homomorphism from our group to S4. And why S4? Well, that's because we're taking this N3 to be equal to 4. Okay, so let's define the following map. So we'll define, I'll call it psi, and it goes from our group to S4. In other words, the group of permutations on 4 letters. And it's defined in the following way. So psi of little g is equal to sigma in S4, where sigma of I equals j if g inverse pi g equals pj. Okay, so we know that if we take conjugates of these subgroups, we just land back on the subgroup. So that's by this condition right here. So we can use that to induce this homomorphism onto the permutation group here. So let's maybe do like a little example here. So let's say our example would do something like this. Let's say we've got an element G from the group, and it satisfies the following rules. So G inverse P1G equals P2. And then also G inverse P3G equals P4. So that's how the conjugation works under this element. And then by this data, we can see what permutation is associated to this element. So in this case, psi of G will be equal to the transposition 1, 2 times the transposition 3, 4. Again, that's because G inverse P1G was equal to P2, and then the same kind of thing for P3. So we've got a homomorphism. I guess you have to check that this is a homomorphism, but that's not too hard. We've got a homomorphism from G to S4. Okay, so let's maybe get rid of this, and then we'll show that that homomorphism has a kernel, and kernels are always normal. Okay, on the last board, we built a homomorphism, which we called psi, from G to S4. Next, I want to notice that the order of G is equal to 144, which is less than 24, which is equal to 4 factorial, which is equal to the order of S4. So again, that's just by comparing numbers. But then this analysis together with the first isomorphism theorem will imply that the kernel of psi cannot equal just the identity element. In other words, this is not an injection. Okay, then why can't the kernel be the whole group? So notice that if the kernel of psi equals the whole group, then that tells us that G inverse P1G equals P1 for all G in G. In other words, every element from the group is just sent to the identity element. So for instance, P1 is fixed under this conjugation, and P2 is as well, and P3 and P4 are all fixed under conjugation by an element from the group. But that contradicts this fact over here, which is the second Sylow theorem. So this is also impossible. So what we have is we have a homomorphism whose kernel is not just the identity element, and the kernel is not the whole group. So we have a kernel to this homomorphism, which gives us a normal subgroup of G, which is non-trivial, making this group not simple. Okay, so now let's maybe get rid of this and we'll look at the last case, which is when N3 is equal to 16. Now we're ready to look at our last case, which is there are 16 Sylow 3 subgroups. So I've written them over there as P1 through P16. Okay, so let's maybe break this into 2 subcases. We're actually gonna do this a few times. So our first subcase will be Pi intersected with Pj is equal to just the identity element. And this is going to be for all ij between 1 and 16. But let's make a little diagram of what's going on here. So let's say our group is this big box here. And then I'm just going to draw a couple of our Sylow 3 subgroups. So let's say this smaller rectangle is P1, and then this rectangle down here is P2. That's the intersection of P1 and P2. And by our assumption, there's only one thing in that intersection, and that is the identity element. Then next, let's maybe put P3 out here. We could put P4 out here. And again, those guys are only intersecting in the identity by our assumption in this subcase. Okay, so if these are only intersecting in the identity, then that means there are 8 elements in each of these Sylow P subgroups, Sylow 3 subgroups in this case, that are not in any of the others. So let's maybe write that here. We've got 8 elements here, we've got 8 elements in here, 8 elements in here, and 8 elements in here. But there are 16 total groups. I've only drawn 4 here because it would get really messy if I drew all 16. But that allows us to count up the number of elements in these Sylow 3 subgroups. So let's maybe make that a notice. So let's notice there are 8 times 16 non-identity elements in the Sylow 3 subgroups. Now we want to look at all of the rest of the elements. And so that would be the identity and then every element that is not in one of these groups. So those are kind of like living out here. So I'll just put some dots out here to show the elements that are not in any of those groups. Like I said, the identity is one of them because we're considering that as not counted here. So let's see how many elements are unaccounted for. So there are going to be 144 minus 8 times 16 other elements. What's that? Well, notice that 16 times 9 is equal to 144. So this is just 16 times 9 minus 16 times 8, but that's equal to 16 other elements. But we also know that there is at least one Sylow 2 subgroup of order 16. Well, we've only got 16 leftover elements after doing this counting, which tells us that there's only the possibility of having one of these Sylow 2 subgroups. So again, by something that we've used before, if we have only one Sylow P subgroup, it is normal. So let's write that down. So the unique Sylow 2 subgroup must be normal. Again, why can't there be more than one Sylow 2 subgroup? Because we don't have enough elements left over after doing this counting process. So now we're going to look at the next case, which is what if we have non-trivial intersection of these Sylow 3 subgroups? For our next case, we're looking at the case when these do not all trivially intersect. But since they all have order 9, the only non-trivial intersection they can have is in a subgroup of order 3. Notice if they completely overlap, then they are the same subgroup and there's nothing really going on there. So in other words, we're going to suppose that there exists Pi and Pj, both Sylow 3 subgroups, such that their intersection contains 3 elements. Then next we're going to introduce some more notation, and that is we'll just call P equal to the intersection of Pi and Pj. So that's going to be a subgroup of our original group that is of order 3. Okay, next we're going to consider something called the normalizer of P and G, and we're going to call that N. So we'll say N is equal to N sub G of P. So let's recall what that is really quick. So that's going to be all elements G in G such that G inverse PG is contained inside of P. So notice if this is the whole group, then P is normal. And so this is like a classical way of creating a new subgroup from an old subgroup. So we've got this old subgroup P, which we created by intersecting 2 of our Sylow 3 subgroups. then we created a new subgroup N by looking at its normalizer. So let's just point that out over here by saying that this is a subgroup of G. Now, before we talk about the order of N, I want to notice that Pi and Pj are both subgroups of N. So let's make that little claim here. So Pi and Pj are both subgroups of N. And why is that? Well, we know that the order of Pi is equal to the order of Pj, which is 9. And so that means that they are both abelian. We know that groups of order p squared, where p is a prime, are abelian. And so since Pi and Pj are both abelian groups, and, well, P itself is going to be an abelian group, then it's pretty clear that every element of Pi and Pj will satisfy this rule right here, meaning that Pi and Pj are a subgroup of this normalizer. But now we can make another little diagram that will inspire a lower bound for the order of N. So let's say we've got N here is this whole box, and then we have P, which is right here. We know that P has 3 elements. P is the intersection of Pi, which is up here, and Pj, which is down here. Pi and Pj both have 9 total elements, so that means that there are 6 left over here that are in Pi but not P, and then 6 left over here that are in Pj but not P. But now looking at this, 6 plus 3 plus 6 is, let's see, it's 15, so that means the order of N must be bigger than or equal to 15. But it also has to divide 144. So the numbers that divide 144 that are bigger than or equal to 15 are going to be 18, 36, 72, or 144. So in fact, we need to look at all of those cases. So I'll go ahead and get rid of some of this, and then we will start looking at those cases one at a time. So in the last board, we determined that the size of this normalizer was 18, 36, 72, or 144. Now we're going to look at each of those possibilities and see that each of those possibilities implies that we have some sort of normal subgroup. So let's maybe start with the easiest case, and that would be if the size of the normalizer equals 144. But that tells us that the size of the normalizer is the same as the size of the group. In other words, the normalizer is equal to the group. But the normalizer being equal to the group tells us that our original subgroup was in fact normal. So we found a normal subgroup of G, so G cannot be simple. Okay, so now let's look at the second case, which would be the size of N equals 72. So that's maybe the second easiest. But that tells us that the index of N in G is equal to 2. But by a pretty standard result, if you have a subgroup with index 2, it is automatically normal. So in other words, N is normal in G. Okay, so let's move to the next easiest case, which would be N equals 18. So let's say the number of elements in N is equal to 18. But notice that 18 factors like 2 times 3 squared or 2 times 9, which means this subgroup N has its own Sylow 3 subgroups. And then let's say that M sub 3 is equal to the number of Sylow 3 subgroups of this subgroup of our original group, which we're calling N. Okay, so we know that M3 must divide 2, given the fact that that's left over after dividing out 9. And we also know that M3 must be congruent to 1 mod 3. But now putting these two things together, the only number that divides 2 and is congruent to 1 mod 3 is 1. So that means that M3 is equal to 1, but that tells us that N has only one subgroup of order 9. But we know that that's just not true by something that we saw on the last board where we showed that Pi and Pj were both subgroups of n. So that actually brings us to a contradiction. This possibility is not possible. So here we get the introduction of a normal subgroup. In 2, we get the introduction of another normal subgroup. And then this third possibility cannot happen. Okay, so it looks like we've got one more possibility to check, and that would be if n equals 36. So let's get rid of this and then we'll do that. Okay, so now we're ready to finish this off. And that would be the size of n equals 36. We checked all of those other cases and saw that they were either impossible or they brought us to having a normal subgroup. Okay, so let's see what we get here. So this tells us that the order of n in G is equal to 4. But that means we can decompose G into the disjoint union of 4 cosets of n. So let's write it like this. x1n, disjoint union x2n, disjoint union x3n, and then finally disjoint union x4n. Now we're going to do a pretty similar trick to something that we did earlier, and that is induce a homomorphism into S4. So let's define phi from G to S4 in the following way. So where phi of little g equals sigma with sigma I equals j if G times xi is in the coset xjn. So we take one of these coset representatives, left multiply by G, it's still in the group, but it being in the group means it's in one of these cosets. It might be in a different coset, and that's how we decide how to define this permutation out of our group element. Okay, so let's maybe do a little bit of an example to see how this is constructed. So let's say that G has the following property. Gx1 is an element from x2n, and then let's say Gx2 is an element from x3n, and then finally Gx3 is an element from x1n, and then maybe Gx4 is an element from x4n. So that kind of stays fixed. So let's say we take a random group element and it takes the coset representatives to the following other cosets. Okay, but notice that that tells us that phi of G will be the 3-cycle 1, 2, 3. Because G of x1 is inside of x2n, G of x2 is inside of x3n, and then so on and so forth. Okay, and now through a method that's very, very similar to what we did before, you can check that this is a homomorphism with a non-trivial kernel. So we've got a kernel of phi, which is a normal subgroup of G. Like I said, we can check that that is non-trivial, giving us a normal subgroup of G, which tells us in all of the possible cases we end up with a normal subgroup of G, meaning that G cannot be a simple group, telling us that there are no simple groups of order 144. And that's a good place to stop.